Okay, so let's continue where we were last time. So last time we were talking about determinants. This time, okay. And do you remember what were the properties? So you have a determinant of any square matrix that's n by n matrix, right? The first property was that the determinant of the identity matrix is 1. Okay. The second property, do you remember the second property? It was that if you switch two rows, no matter what rows you switch, that will change the determinant by a factor of -1. The determinant changes sign. And then there's one more property, which is that the determinant is linear in each row. So what does that mean? So it really means like two separate things, but they can be combined if you have determinant of some matrix. Let's just do a 3 by 3. Let's say you have row 1 and row 3, say, and let's say that the second row is some constant times some vector plus another constant times a different vector. Well, the linearity in each row says that I can pull CV and DW apart. So this is equal to the determinant of the 3 by 3 matrix, where I keep the other rows the same. But I have CV here, and then plus the determinant, where I have DW here. And that's from the additivity part. And then the other aspect of linearity is that as long as you keep the rows the same, you can pull a constant out of a row. So this is going to be equal to C times the determinant of this matrix, where you have row 1 and V and row 3, and then plus D times the determinant of this matrix, where you have row 1 and then W and then row 3. Right, so that's linearity in each row. Well, this case I was using linearity in row 2, but you could have done the same with rows 1 and 3. Okay, and the important thing is that these three characterize the determinant, right? So let's just look at some properties of this. Let's just look at an example first. It's sort of a property, but we'll see the general property later. Let's say I have a 2 by 2 matrix, A, B, C, D. Okay, so the determinant of this is AD minus BC. And let's say I multiply this matrix by E, some constant E. And well, what that's going to do is that's going to change each of these entries by multiplying it by E, right? Now, what's this determinant going to be? Well, one thing you can do is just use the formula, okay, except it's EA times ED minus EB times EC. Another thing you can do is you can use the fact that you can pull out an E from the first row, and you can pull out an E from the second row. So you're going to get E squared times the determinant of A, B, C, D. So actually, the determinant of E times a matrix is E squared times the determinant of that matrix, if that matrix is a 2 by 2 matrix. So what do you think is going to happen if you multiply? So what would be the determinant of C times an n by n matrix A? Well, you see what's going to happen? If you have n rows, and you have C times, A11 to C times A1n, and then you go down to C AN1, C ANN, this is going to be equal, so this is equal to this, and then you can pull out a C from each row. And how many rows do you have? N. So this is going to be C to the n times the determinant of the original matrix. So this is C to the n times the determinant of A. So if you multiply a matrix by a scalar, the determinant changes by that scalar raised to the nth power. Okay, so the determinant of CA is not the same as C times the determinant of A. It's C to the n power times the determinant of A. Okay, let's look at some properties of the determinant. I guess we could just say that this is section 5.2, properties of the determinant. So I'm introducing determinants differently than how the book does it. So I'm sort of mixing 5.1 and 5.2. So the determinant. Well, we're not going to prove these properties. I'm just going to say them. The first property, one property, is that the determinant of A times B is the determinant of A times the determinant of B. Okay, of course, A and B have to be square matrices. So if A and B are n by n matrices, and of course they have to be the same n because I have to be able to do A times B. And so let's just parse through the sentence. So A times B is a matrix, right? That's an n by n matrix. And the determinant of that matrix is a number. So the thing on the left that I have is a number. And the determinant of A is also a number. Right? This is this fancy thing you can do where you can just... Anyway, the determinant of A is also a number, and the determinant of B is also a number. So I have a number is a number times a number. Okay, and it's important to say that A and B are square, because you could, it's possible that, A is a 2 by 3 matrix and B is a 3 by 2 matrix. Well, A times B would be a square matrix. If A was a 2 by 3 matrix and B was a 3 by 2 matrix, A times B would be 2 by 2. And that does have a determinant, right? But A and B individually don't have determinants because they're not square matrices. So in order for the sentence to make sense, that this is equal to the right-hand side, that this is equal to this, you have to make sure that A and B are square matrices. Otherwise, the things on the right would not be defined. Okay. And this actually leads to another way of seeing this property above, because can you think about, if I have a matrix A and I multiply it by a constant C, so I scale every entry, how can I represent this as a matrix times A? What matrix times A is the same as scaling all the entries by A? It's if you put C on the diagonal. If you put C on the diagonal, then it scales each row by a factor of C. And since A is n by n, this is an n by n matrix, and then you can just use, right? So using this property, the determinant, let's call this matrix, well, this would be C times the identity, right? So the determinant of CA is the determinant of C times the identity, right, this matrix, times the determinant of A. And do you remember for a diagonal matrix, or more generally, upper triangular matrix, what's the determinant? I can multiply the diagonal entries. And I have n c's, so this is going to be c to the n times the determinant of A. So I could also have used this property, like the multiplicativity property of the determinant, to also get this result, that this is equal to this. Okay. So another property is that if A is invertible, well, can we figure out what would happen? If A is invertible, there's some inverse, right? A times A inverse is the identity. And now we can, what can we do to both sides to introduce determinants? We can take the determinant of both sides. So the determinant A inverse is equal to the determinant of identity, and that's, what is that? What's the determinant of identity? 1. And now, do you see what I can do with this guy, the determinant of this product? I can do the product of the determinants. So this is equal to the determinant of A times the determinant of A inverse. Right, so from here to here, I'm using this property. Okay, should I just call it like star? So by star, I can split up the determinant like this. So this times that is equal to 1. And now do you see what can either, so I have this number times this number is equal to 1. So what does that tell you about the numbers? They're reciprocals, right? The determinant of A inverse is 1 over the determinant of A. And also from this fact that the product of this and this is 1, you know that neither of these can be 0, right? So, okay, so we actually have 2 facts. So here's one fact. And another fact is that if A is invertible, then the determinant of A can't be 0. Oh. Now what happens if A is not invertible? Well, if you have a non-invertible matrix, what can we say about its determinant? Remember, when you row reduce A, to get echelon form, what has to happen if your matrix is non-invertible? What's the bottom row going to be? 0 row, right? The echelon form has a 0 row on the bottom. And remember, one of the things that we talked about last time is that you can use the linearity property to replace one row by that row minus constant multiple of a different row. So basically, as long as you don't multiply the row by a constant, the determinant doesn't change. And so you can do elimination and keep the determinant the same. You know, if you don't have to swap 2 rows or anything. That just changes the sign. But the determinant of A is more or less, it's going to be, plus or minus the determinant of the echelon form. And if you have a matrix with a 0 row, right, and you have stuff above, what's the determinant of this guy? It's 0, right? Because you can do cofactor expansion along the bottom row, so you're going to get 0 times, some determinant, minus 0 times another determinant, etc. It's going to be 0. Okay. And then one more property about the determinant is that the determinant of A transpose is equal to the determinant of A. Okay. So these facts are facts that we won't prove. So the main things we haven't proven is this multiplicative property, and that the determinant of the transpose is a determinant of A. And one thing we haven't proven is why the formula that we gave last time works. So can we just review the formula for the determinant again? Let's say you have, what's a good example? Okay, so let's do an example of this determinant. 1, 5, 2, 0, negative 3, 1, negative 1, 2, 1. Okay, so what is this value? So remember, these bars mean that it's the determinant. Okay, so what is this number equal to? And we can do cofactor expansion along any row or column. The fact that you can do cofactor expansion along any column has to do with the fact that the determinant of A inverse is the determinant of A, because you can switch the rows and the columns. So how would we do this? We would pick a row or a column we want to do cofactor expansion along, and it helps to do one that involves 0. So I see a 0 here. I see a 0. I see a 0 there. Oh, wow. 0 there. So it helps. It's easier if you do cofactor expansion either along the first column or the first row, because the 0 means that when you use the formula, you're not even going to have to do that determinant. Right. Okay, so let's say let's look at the second row. So let's do cofactor expansion along the second row. So you're going to get 0. Now remember, there's this plus minus plus thing going on, right? It's an alternating sum. So remember, for this matrix, I'm going to have this grid. I need to keep track of the size that I'm using. So I have a plus, minus, plus. It always starts with a plus and alternates like this. So actually, I have a minus 0. Well, it's not going to matter because it's going to be 0 at the end, but let's just write it down. So minus 0 times, now you get rid of the first row the second row in the first column, you're going to get the determinant of 5, 2, 2, 1. Right? And now I'm going to have a plus because of this number here. So I have a plus, and then I have a negative 3 there. And then what matrix do I put here? I think I'm going to have 1, 2, negative 1, 1. Right? Because I'm getting rid of the second row and the second column. Let's erase this. And then finally, I have a minus, again, because of this minus sign here. So minus, and then a 1 here, and then I get rid of the second row and the third column, and I'm going to get 1, 5, negative 1, 2. So this determinant is equal to this. And now I just need to figure out what this is. So this is going to equal, so this guy is going to be 0 because I have 0 times some number. And then this is going to, so 0, and then I have a plus negative 3, so minus 3 times this determinant. So I'm going to get 1 times 1 is 1, and then minus negative 1 times 2 is negative 2. So I have 1 minus negative 2 makes 3. And then I have a minus 1 times 1 times 2 is 2, and then minus negative 5, that makes 7. So my final answer is negative 16. So that's the determinant. Okay, now what's the general formula? And again, you didn't have to do expansion along the second row. You could have done the first column, or actually any column or any row, but the reason why I wanted to do it along the second row is because I have a 0 here, and so when you think about it, you really only have to do 2 of these smaller determinants, right? I mean, if you did expansion along the first row, you're going to have to do 3 separate 2x2 determinants. So it's just like a good strategy to take advantage of any zeros you have. Okay, can we write down the general formula for the determinant of A? So let's say I have A is, A11 to A1n, and then AN1 to ANN. And let's say I want to do cofactor expansion along, well, last time I gave the formula in terms of cofactor expansion along the first row, but what if you wanted to do it along row I? So the determinant of A is, can we just ignore the pluses and minuses for now? We'll come back to that later. If we didn't have to keep track of the plus and minus, what would the formula be? I'll start with, so let's say I have row I, and I want to expand along this. So my first number is A sub I1. I'm going to use a different color. And I'm going to end at A sub IN, right? So this determinant is going to equal this number, AI1, times the determinant of what I get when I remove row I and column 1. So that's, I called it, last time I called it MI1. Right? And then plus, because again I'm ignoring the signs for now, then I go on to the second number, which is AI2, since I'm doing row I, and then the determinant of the matrix I get when I remove row I and column 2, and that's MI2. And then I just keep going until I get to the end. So AIN times the determinant of M sub IN. And this Mij is the matrix. It's the n minus 1 by n minus 1 matrix I get formed by removing row I and column J. Okay? Okay, so now we have to figure out alternating the pluses and minuses. So how does that work? Well, let's think about this grid, the pluses and minuses. Let's just do 5. So it alternates like this. Okay. Now, what do you notice? So this term is the 1, 1 term, right? It's row 1, column 1. And this would be the 1, 2 term. This would be the 1, 3 term, etc. Right? So, for instance, for this matrix that's 1, 5, 2, I have to do plus 1 times this determinant here, and then minus 5 times this other determinant, plus 2 times the remaining determinant, and so on. And here's entry 2, 1, here's 2, 2, okay, and so on. Now, what do you notice about where the pluses and minuses are? If you add the 2 subscripts, do you notice something? The odd ones are where the minuses are. Because for this one, that's an entry 1, 2. 1 plus 2 makes 3. And like here, 1 plus 4 makes 5. And then if you look at this minus, that's the 2, 1 entry. 2 plus 1 is 3, and so on. And then the pluses are where it's all even, where the sum is even. And so I'm going to have to do a plus when I plus j is even, and a minus 1 when I plus j is odd. So how can I incorporate that here? You see, what can I do? What power can I raise -1 to so that when I plus j is even, I get 1, and when I plus j is odd, I get -1? Oh, I think I can use the exponent I plus j. Is that right? When I plus j is even, this is 1. When I plus j is odd, this is -1. And so that tells me how I can modify this definition to be correct. Let me give myself more space. I need a -1 to the I plus 1 here, and a -1 to the I plus 2 here, etc. All the way to -1 to the I plus n. Now that I have this is the correct formula. Can I just put a box around this? Okay, let's put a box around this. Can I just write it in a more compact form? I'll use the summation notation, the determinant of A, if I expand along row I, is the sum of -1. Now I'm going to use the symbol j. J is the variable that ranges from 1 to n. So j goes from 1 to n. -1 to the I plus j power, and then A sub ij, and then times the determinant of the matrix M sub ij. Okay, let's put a box around that. So this is the formula that you sometimes see in books. And so this is the cofactor expansion along row I. The cofactors are, I don't use that term very much, but it's the -1 to the I plus j times it's this constant times this determinant. Those numbers are called cofactors. So we won't use that terminology very much, but just in case you're wondering what a cofactor is, that's what it is. So I'm trying to just clarify that. That's -1 when I plus j is odd, and +1 when I plus j is even. And that's why I have this -1 to the I plus j. Okay, let's see if I have time. Okay. So let's take a look at some more complicated examples. Oh, should we do a 5x5 example? Oh, why not? Let's do a 5x5 example. So this example summarizes a lot of the different techniques that we use. So compute this determinant. Okay, so 6, 3, 2, 4, 0. 9, 0, -4, 1, 0, 8, -5, 6, 7, 1, 2, 0, 0, 0, 0, 4, 2, 3, 2, 0. Okay. Compute this determinant. Okay, well, this is a 5x5 determinant. Now, if the numbers were just random, right? If I had 25 random numbers, this determinant would take forever. But again, using that strategy that we had, when you look at this, don't just automatically work with the first row and do a co-expression like that. First, take a look and see, is there a row or a column that makes the cofactor expansion easy? I think there's two of them, right? It seems like a good strategy would be to use row 4, or we could use column 5. Let's use column 5. So let's use cofactor expansion along column 5. Is this going to bleed through? No. Let's use cofactor expansion along here. Okay, so what do we get? This equals. And now I have to think about my grid, right? So I have a plus, minus, plus, minus, plus. So I have a plus, and then a minus, a plus, minus, plus. Well, I'm going to get 0 times I'm going to get 0 times this determinant, right? Plus 0 times some other determinant. Well, it's, whatever, minus 0 times that determinant, and then plus 1 times what determinant? I remove row 3, column 5, 6, 3, 2, 4, 9, 0, -4, 1, 2, 0, 0, 0, 4, 2, 3, 2. Okay, so now I have a 4x4 determinant. And now what should we do? I think now comes this row, right? The third row. Let's do cofactor expansion along this row because of these zeros. So what am I going to get? equals. And so now when I have this smaller determinant, when I'm using the pluses and minus grids, I'm starting over, right? So the 6 is still going to be, like I'm still going to have this plus minus pattern in the same way, like this. Right. So if I want to do expansion along row 3, I'm going to have a plus. So I have a plus 2 times a 3 by 3 determinant. And then the other terms are going to be 0. So 2 times the determinant of 3, 2, 4, 0, negative 4, 1, 2, 3, 2. And should we just do cofactor expansion again along the second row? Okay, why not? Let's just do cofactor expansion like this because of the 0. So now I'm going to get, let's see, 2 times, so I have a minus here, and then a plus, negative 4. So negative 4 times this determinant, 3, 4, oops, determinant, 3, 4, 2, 2. And then minus 1.
Okay, this room is booked at 11:35.
Oh, okay.
Yeah.
Sorry, okay.
And they're here, they need the time.
Oh, okay. Okay. Sorry, I need to go. Negative 1 times this determinant, 3, 2, 2, 3. And then once you compute this determinant, you get 6. And that's the answer. Okay, great. I'll continue later.